Well, students, it's been a long time since we met, right? I think I have not taken a class of yours since maybe July, right? Okay, but we had completed many lessons, right? So we had completed solids, we had completed solutions, we had completed kinetics, chemical kinetics. Then I think we had completed E block, surface chemistry, I believe, surface chemistry, P block. Okay. Then I think we had done coordination chemistry. And also we have done D block, right? D and F block. So all these chapters were done. And I think I had revised that also. Again I thought it has been a long time. Why not again revise these chapters? Okay. So let's start with some revision. So it is better to keep in touch because these lessons were completed right from the month of March, right? Solids we had completed in the month of March. Again we did it in maybe June, right? So let us do the revision now. And let us do it from solids. Okay, the first chapter. Now in solids, the first thing you should know is the classification. So classification of solids. So solids are classified into two types. Is it? First one is crystalline. And the second one is amorphous. Right? So the first question you might expect from in solids is what are the differences between a crystalline solid and an amorphous solid? So the basic difference between these two is what? The arrangement of particles, isn't it? In a crystalline solid, you have a long range order of arrangement of the particles. Whereas in amorphous, what happens? There is random arrangement of particles, or we say they have a short range of arrangement of particles. So this is the basic difference between the two, or what differentiates solids into crystalline and amorphous. It is the type of arrangement of particles in that. So in crystalline, you have a long range order of arrangement of particles, whereas in amorphous, we have a short range order. So you should write here, first difference between the two is what? Long range order. Whereas this is short range order. So because of that, what will happen? These are having more pronounced properties than this. Okay. So the long range order of arrangement makes them have very sharp melting points. So crystalline solids will have very sharp melting points. Whereas the amorphous solids will, when you heat them, what will happen? They will soften and then start running. In the sense, they slowly soften over a range of temperature and they will convert into fluids. So therefore, another name for these amorphous solids is also pseudo-solids. Okay, so they have, they melt over a long range of, when you heat them for a long period, you can say. Okay, or they start fusing. Therefore, they won't have very sharp melting points. Their melting points are very, very low. So, low melting points. Okay, so I won't count this as a difference. So if at all the question comes, give any three differences between crystalline and amorphous, it is better to give this one as one, no need of giving this one. The second can be a particular difference that is related to this. So what happens when you cut a crystalline solid into two pieces? You get two pieces, right? They also will have even surfaces. Okay, but when you try to cut an amorphous solid into two pieces, you will get the two pieces which will have irregular surfaces. Here you will have very nice surfaces when you cut them, but this will not give you regular surfaces when you cut them into two. So these two are related to this particular first difference. Then the second you can give is, these are anisotropic in nature. Crystalline solids are anisotropic in nature, whereas amorphous are isotropic in nature. This one. So I would prefer you to give this one as a difference. This is another difference that you can give. Okay. After that you can say they have sharp melting points, they have very low melting points. Okay. And you can give the cleavage property, that is, when cut into two pieces, crystalline solids will have smooth surfaces, whereas you get irregular surfaces when you cut amorphous into two pieces. Okay. Then the third difference as far as heat of fusion goes. So they have definite heat of fusion, but this do not have a definite heat of fusion. Like this you can give, because most of the time it will be any three differences. So this one is required, this one also is required. Okay. After that you can give any difference you want. So this is the difference between a crystalline and amorphous solid. Then if we go to classify, we don't have classification for you for amorphous solids, but we do have classification for crystalline solids, right? So crystalline solids are further classified into four types. First one, molecular. Second one, ionic. Third one, metallic. And the fourth one is your covalent or network. Right? So you can further classify the crystalline solids depending upon what type of constituent particles they have. Okay. Now, if the constituent particles are molecules, then you get a molecular crystalline solid. If they are ions, then it is an ionic crystalline solid. And if they are metal atoms or ions, then it is metallic crystalline solid. And if there is the constant particles are atoms, then it is covalent crystalline solid. Okay. So molecular solids are further divided into three types. First one is non-polar. Second one is polar. And the third one is hydrogen bonded. Okay, so molecular crystalline solids are further classified into three: non-polar, polar, and hydrogen bonded. So here the constituent particles are held by very weak forces, like for example a dispersion force that will exist holding the molecules together. Therefore you get a non-polar molecular crystalline solid. But if the force is little bit stronger, like for example a dipole, if there is a dipole-dipole interaction, okay, between the dipole force is holding the molecules together, then you get a polar crystalline solid. And if there is, because when you come to the third one, the hydrogen bonded, obviously there is a hydrogen bond, right? Now, you know, this is a proper chemical bond. Now, these are not chemical bonds, they are simply forces of attraction. Okay. Okay. Coming to ionic, the ionic bond is the force of attraction, right? Or it is an electrostatic force of attraction between the ions, because ionic solids, in ionic solid, the constant particle is the ion. Okay. So positive ion and negative ion, like that. So there is an electrostatic force of attraction between opposite charges there. Therefore, what happens as you go from here to here, what happens? The properties and everything go on increasing. Then the metallic solids in the textbook are explained using the electron C model. Okay, so we have a sea of electrons, right? So that model is given. Or the properties of a metallic solid is explained using the electron C model. Okay, so this is the overall classification of the crystalline solids. Okay, so first I have put together everything in one. So solids are divided into crystalline, amorphous, and crystalline are further divided into 4: molecular, ionic, metallic, covalent. Then molecular are further divided into 3: non-polar, polar, and hydrogen bonded. So this is with respect to classification. Okay. So after the classification of solids, you have to come to the structure of a solid. Then you have to know what is meant by a lattice or crystal lattice. Right. So if I want to draw a rangoli, what I do? I normally put points like this, right, in one dimension. Like this, I put points. 4 by 4 or 5 by 5, whatever it is. Then I join those points like this. To get a particular figure. So this is called, putting points in space in one dimension, and joining those points in straight lines, you are able to get a figure, which is called as a rangoli. In a similar manner, if I am allotting these points in space in 3 dimensions, and when I allot these points in 3 dimensions, where each point is occupied by the particle, then this 3-dimensional arrangement of points in space, where each point is occupied by a particle, and if joining these points, if I are able to get a structure of the crystal, then that arrangement of points in space is called as a crystal lattice. So crystal lattice is simply the 3-dimensional arrangements of points in space, where each point is called as a lattice site or lattice point, and that point or site is occupied by a particle, and joining those points in straight lines or with straight lines, if I am able to get the structure, that is called as a crystal lattice. Okay, so there are 14 possible crystal lattices. Okay, and these were given by a French mathematician called Bravais. Therefore, they are called as Bravais lattices or lattices. Some call it as lattices, some call it as lattices, whatever. So this is the first thing that you have to know, what is meant by a crystal lattice. Then comes the unit cell. So what is meant by a unit cell? See, just like an atom is the fundamental particle of matter, cell is the fundamental particle of biological life. Similarly, the smallest fundamental unit of a crystal is called as a unit cell. This unit cell, when it is repeated in all directions, will produce the crystal lattice or the crystal. So the fundamental basic unit of any crystal, which when repeated in all directions produces the crystal, is called as an unit cell. Understood? So every unit cell is characterized by two important characteristics. So I will draw a picture of the unit cell, and as I told you, every unit cell is characterized by two main characteristic features. So if this is a okay. So this is a diagram of the unit cell. Now each unit cell has the edge lengths A, B and C. These edge lengths may or may not be mutually perpendicular. Okay. So these are the edges of the, now I have taken an unit cell. So there are three edges. So this may or may not be mutually perpendicular. Okay. Then there are angles between these edges. So every unit cell is characterized by the edges or edge lengths A, B and C, and this may or may not be mutually perpendicular. Okay. Then comes the angles between A and C. This is alpha. Between C and B, it is, I'm going to go in anti-clockwise direction, sorry. Between A and B, like this. So this is alpha, this is beta, this is gamma. Okay. A and C, it is alpha, and C and B, it is beta, and B and C, it is gamma. Okay. So these are the edge angles. Okay. So every unit cell is characterized by the edge lengths A, B and C, which may or may not be mutually perpendicular, and the edge angles alpha, beta and gamma. Okay. So depending upon this, you will get different types of unit cells. Now after the unit cell comes types of unit cells. So there are basically two types of unit cells. The first one is primitive. The second one is center. Okay. So what is a primitive unit cell? In a primitive unit cell, the particles will be occupying the corners. So, if there are particles present at the corners of this unit cell, there are 8 corners, so 8 corners will be occupied by the 8 particles. Then it is called as primitive unit cell. Okay. Centered means other than those at the corners, there will be particles on any other surface or on any other part of the crystal. Therefore, in center there are 3 more types. First one is BCC, then FCC, then ECC. So you have a body centered cube, then you have a face centered, and you have an end centered. So in centered, what happens? Other than those at the corners, there will be particles on any other part of the crystal. It can be on the surface, on the face, it can be inside the crystal, like that. Okay. So let us see what is meant by BCC. In BCC, 8 particles are there at the corners. So if 8 are there at the corners, it is primitive, isn't it? So here 8 are there. Other than these 8, there is one particle at the center here. So totally there are how many? 8 plus 1. 9. Here there are 8. So this is at the body center. So it is independent. It is not touching anybody. Okay, so this is independent because it is inside. So what is this FCC? So FCC means face centered. So there are 6 faces, right? So one particle will be present on each face other than those that are present at the corners. So okay, these are 8 plus here there are 6 faces. So here one, behind one. So totally how many now? 8 plus 6, 14. ECC means there are 8 at the corners, there will be one at one end which will be shared with another unit cell. So therefore it is called as end center. Okay, so there will be one at the end which can be shared with another. Then this becomes end center. So these are types of unit cells. You have two major categories. One is primitive, another one is centered. Primitive means if the unit cell has 8 particles occupying the corners. In centered means other than the 8 at the corners, there will be particles on other places. Okay. So there you have 3 types: body centered, face centered, and end centered. Okay. So body centered means totally 9. Okay. So here there are 8 particles at the corners, 1 at the body center, totally 9 particles. In FCC there are 8 at the corners, 1 on 6 faces. So totally 14 particles. Here we have 8 at the corners and there is 1 particle which is at the end, which can be shared with another unit cell. Okay. So I have covered what? Classification of solids, what is meant by a crystal lattice, what is meant by a unit cell, and types of unit cell. So this is first part of your revision. Okay. So I will carry in the next class.